In the heart of the sun, a cosmic inferno rages, powered by a breathtaking dance of atoms. It's a process so powerful and awe-inspiring that it's hardly possible for us to grasp. It's called nuclear fusion. This captivating act involves the fusion of light atomic nuclei, typically hydrogen isotopes like deuterium and tritium, to create a heavier nucleus, usually helium. The result? A colossal release of energy, the very life force of stars. Fusion powers the sun, radiating light and warmth across the cosmos. In fusion's fiery embrace, nuclei overcome their natural repulsion through unimaginable heat and pressure. As they collide, they merge into new elements, unleashing energy according to Einstein's iconic equation. It's the ultimate cosmic alchemy, where matter transforms into pure energy without the lingering radiation nightmares of fission. Let us now turn to nuclear fission. Here, instead of merging, heavy atomic nuclei split into smaller fragments when bombarded by neutrons. This process releases a torrent of energy and more neutrons, triggering a self-sustaining chain reaction. Fission powers our nuclear reactors and, alas, atomic bombs. But it comes with a sinister caveat, a slew of radioactive waste that remains hazardous for centuries. Here's where the excitement takes center stage. Fusion, in theory, is far more efficient and cleaner than fission. It produces minimal, long-lived radioactive waste, and its fuel sources, hydrogen isotopes, are virtually boundless. It's like tapping into the endless cosmic wellspring of energy. However, there's a catch, and it's a doozy. To unleash fusion's fury, we must recreate the sun's searing temperatures and pressures right here on Earth. It's akin to trying to bottle a star's essence. Imagine containing a seething plasma at millions of degrees Celsius without letting it melt through its earthly constraints. That's the challenge of controlling fusion. Now, imagine if we could harness this very process, recreate it on Earth, and unleash a revolution in our energy production that could change the world as we know it. How could this spectacular feat become a reality? Forging the inferno. Nuclear fusion, the same process that fuels the sun, demands conditions that would make most of us cringe. We're talking about temperatures in the millions of degrees Celsius and pressures that would crush mere mortals. On Earth, we're striving to create these conditions in something called a fusion reactor. Picture massive machines or wondrous stellarators. They wield the power of colossal magnetic fields to trap and compress a seething plasma of hydrogen isotopes. This is the fiery crucible where fusion's magic happens. Alternatively, imagine facilities where potent lasers converge on tiny hydrogen-packed pellets, triggering fusion through sheer force, sustaining the cosmic fire. But the real challenge isn't just igniting fusion, it's keeping the flames alive long enough to generate more energy than we put in. We call this moment ignition, and it's the key to unlocking practical power. Taming the wild energy. Fusion generates a torrent of high-energy neutrons, which could wreak havoc on reactor components. To harness this cosmic fire, we must develop materials and engineering wizardry that can withstand the relentless barrage of radiation and the searing heat. Fueling the future. Our stars on Earth hunger for fuel. Deuterium, a hydrogen isotope, can be harvested from water, while tritium, another vital fuel, is born from lithium. Securing a steady supply of these celestial fuels without ecological woes is imperative. Dealing with stardust. Fusion is kinder to the environment than its fission cousin, but it's not without its waste. We need to devise ingenious ways to manage the byproducts and ensure they don't linger for millennia. Balancing the books. Fusion reactors are feats of human ingenuity, but also dauntingly complex and costly. For fusion to shine as a practical power source, it must prove its cost-effectiveness compared to other energy options. The guardian of safety. In the realm of fusion, safety reigns supreme. We must guarantee that these marvels of science can withstand the unexpected, malfunctions, natural disasters, and more without compromising lives or the planet. And there you have it, the quest to harness the power of the stars and transform our energy landscape into something extraordinary. If we succeed, fusion energy could be the cosmic fire that propels us into an era of clean, boundless, and sustainable power, leaving behind the shadows of our fossil fuel past. While commercial fusion power plants may still be a galaxy away, the journey promises to be one of humanity's most thrilling adventures. Well, there are several remarkable projects currently underway, each with its unique approach, pushing the boundaries of science and engineering. So let's embark on this electrifying expedition to explore the fusion frontiers and find out which one is furthest along. ITER, the Titan of tokamaks. Picture a colossal magnetic donut. This massive international collaboration is building the world's largest tokamak in southern France. It's a magnetic confinement device that aims to replicate the high temperature and high pressure conditions needed for nuclear fusion. ITER will use a mixture of deuterium and tritium as fuel and generate a whopping 500 megawatts of fusion power. It's a crucial step towards demonstrating the viability of nuclear fusion as a practical energy source. ITER is well underway and has made significant strides in construction. It's often considered the frontrunner in the fusion race. NIF, the laser luminary. Imagine a laser so powerful it can compress and heat a tiny pellet of hydrogen to conditions hotter than the center of the sun in an instant. That's the National Ignition Facility in the United States for you. NIF employs inertial confinement fusion technology using a barrage of powerful lasers to ignite a small fuel pellet, driving it to fusion conditions. NIF has achieved some significant milestones, but has faced challenges in reaching sustained ignition. It continues to push the boundaries of ICF research. Spark, the stellar startup. Hailing from MIT's Plasma Science and Fusion Center, Spark is a smaller, more agile contender in the fusion arena. It's an experimental tokamak designed to pave the way for compact and economical fusion reactors. Spark aims to demonstrate net energy gain, a milestone that would revolutionize fusion's future prospects. It uses high-temperature superconducting magnets to boost performance. Spark is still in the design and development phase, but represents an exciting approach to fusion. Wendelstein 7X, the Stellarator star. Don't forget the Stellarators. Wendelstein 7X in Germany is the world's largest stellarator, a twisty, donut-shaped magnetic confinement device. Stellarators like Wendelstein 7X offer advantages in terms of steady-state operation and reduced risk of plasma instabilities. This project has demonstrated impressive plasma performance and is continually improving its capabilities. Alongside these international projects, private companies like TAE Technologies, Tokamak Energy, and others are making waves in fusion research, often with innovative and proprietary approaches. Private ventures often bring agility, novel ideas, and unique technologies to the fusion race. So, which project is furthest along? ITER, the Titanic tokamak, currently takes the lead in terms of size, funding, and international collaboration. However, the fusion saga is far from over, and these projects, each with its captivating storyline, are racing towards a future where the dream of limitless clean energy may finally become a dazzling reality. Did you like this video? Then here are 2 more for you. If you don't want to miss any more exciting videos about our incredible world, subscribe to the channel and activate the bell.